Today, we are joined by Naeem Turner-Bandele, PhD, founder and CEO of Latimer Enterprises, and an energy and electricity systems researcher. Naeem works at the intersection of grid operations, power system modeling, and energy policy, focusing on how electricity systems actually function in the real world. This conversation is not about net zero slogans, but about constraints, trade offs, and what it really takes to run reliable, affordable power systems while decarbonizing. Naeem, thank you for joining me today.
Thank you so much for having me. It's a pleasure to be here with you and your audience.
Thank you. My pleasure. So let's start maybe with your background for some context for our audience. You come from a deep technical background in electricity systems. Before we dive into specifics, how do you describe your work today? And if you could tell us what problem are you most focused on solving?
Yeah, absolutely. So, my work is at the intersection of both the deep technical energy, electricity work, but I also try to incorporate strategic financial insights. As you mentioned, I have a PhD, but I also have an MBA. So, questions about finance, strategy, policy are also at the heart of the work that I do. So, my company, Latimer Enterprises, we do a few different things. First, focus on building digital solutions or tools to help individuals, uh, business owners, organizations, those could be renters, managers, property owners, really understand and make more informed decisions related to energy. The second thing that my business does, Latimer Enterprises, we do advisory and research work. So that draws on my background as a researcher to help inform clients on things that they might not be thinking about that they need to know related to energy usage. Good example of that is I did some work last year with a client who was building over 19,000 square foot residential home in the state of Indiana, so huge property. And one of the things that they'd not been made aware of is the energy usage of that home. The architect, the builders really didn't clarify and walk through those things with them. So I was brought on to the project to advise the client on the ways in which they could reduce the energy usage of that home so that when the bills hit, they would not, one, not be surprised by what they saw, but two, also have some tools and strategies for managing that. And then the third thing that my business does is to do a lot of training and education work. I try to ensure that youth and organizations are informed about how energy and electricity systems work. And towards that, have a K through 12 energy education program that I've recently been piloting and looking to scale in a much wider way later this year. So that's what my business does. But to go back to me for a second, to give your audience more context about who I am, they may hear that I have a PhD and MBA and think that I was someone who was gifted at an early age and that I had real talent for math and science. That's not my story at all. When I was in elementary school, middle school, high school, math and science were not my best subjects. You could go ask the teachers I had at the time if those were my best subjects, and I think they would routinely tell you no. And if you ask friends and family who knew me, when I was 16, 17, 15, 16, 17, they would have told you, Naeem, an engineer? Like, absolutely not. It wouldn't have come up on the radar. So how did I get into this space? I was a pretty good football player or soccer player back when I was a teenager. And eventually I hit a point being here in the United States where I realized that if I wanted to really improve, if I wanted to pursue a dream that I had of being a professional soccer player, being able to play and be teammates of athletes like the Lionel Messi's, the Ronaldinho's of the world, I needed to leave the US because this simply is not the best place to play soccer and to learn soccer. So at the time, I've been really inspired by Brazilian soccer, Brazilian football. All of my favorite footballers are Brazilian. And so knowing that, I was able to get connected through someone who knew Brazilian soccer very well and was able to go live abroad and train abroad at an academy in Brazil called Desportivo Brazil in the state of Sao Paulo for great several months. And then I went to other academies and spent about a year or so pursuing this dream in Brazil, trying to play professional soccer. Now, along the way, while I was in Brazil at that first academy, Desportivo Brazil, one of the things I noticed is that this campus that I was in, because for listeners or watchers who don't have context, never seen one of these academies, they're essentially like fortresses. So when you think about football, this it's really one of the main exports of Brazil. So they do their best to protect these footballers and to ensure that they have every need they could possibly have. So they'll build these massive facilities that have lots of security. They're protected by several feet high fences, barbed wire, and they try to keep everything contained inside. As part of that, the academy had a backup generator, a diesel backup generator. And so there would be times, well, actually pretty frequently, where the power would go out at the academy and in the surrounding community. But we had a backup generator, so we continued to have power while the surrounding community nearby didn't have power. And that started to strike me as very odd. And it became a catalyst for what I do now. Now, eventually, I was able to make connections between what I saw at that academy, this more affluent area, footballers who are well taken care of, having access to power, and other people not having access to power, and drew those connections to a much more global lens, made connections to things I saw back home in my own communities, thought about family members that I know and the places that they live in, and what disparities in energy and electricity access look like for them. And so unfortunately, I had a concussion. It's a very serious concussion during my Brazilian soccer journey that required me to stop playing football altogether. But that Brazilian football experience became a catalyst for what I do now because like I said, I made those connections between energy and electricity access and disparities and figured out that this was something I wanted to pursue to figure out how to reduce. And then I went on to get those other degrees we mentioned that enabled me to start the company that I'm running today that does the different things that I mentioned at the start of this introduction.
Thank you very much for that introduction and explanation. I was especially interested in how your academic training translated into applied real world decision making. So you
Yeah,
set a clear picture. Thanks for that.
you're welcome.
So maybe now let's talk about electricity versus energy, because I think it's very important to make this distinction. A lot of public debate treats energy as a single bucket. From a systems perspective, why is electricity, in your view, fundamentally different from other energy uses, let's say, and how does that distinction matter?
Yeah, that's a great question. I'm glad you've decided to highlight that because I think there is an important distinction. When we talk about energy as a whole, we're primarily thinking of our power grids, our electricity grids, and we're also thinking about transportation. Those are kind of the two big buckets that come into focus for people on a day-to-day basis. So those are separate lenses. But even within electricity, there's a broader energy discussion. So when we think about power grids or electricity systems, they're very complex networks, interconnect networks that can be subdivided into primarily three areas. You have generation, which are those large power plants that use different energy sources. That's where that variety of energy conversation comes into play. They convert that energy into electricity, then they send that electricity over huge lines called transmission lines, and then that electricity is then stepped down where the voltage is reduced in order for it to be at a safe level to go into our homes and businesses. So that's the distribution process. And you can think about it kind of like the way in which you get a package delivered to your home. Somebody in a factory makes that package. They produce the goods for you and other people, whatever goods are inside. Then they send those goods, they ship them over long distances, sometimes internationally. That's akin to transmission. And then eventually a delivery driver in a van or a car delivers that package, that good, that product that was produced all the way in a factory to your home. So electricity is the same way in that sense. So like I said, you see there are a lot of different parts that come into electricity and how it's different. So it encompasses both different energy sources and their electricity specific elements. But then there's also, again, that separate part of energy with transportation that makes this a much more nuanced discussion that sometimes people miss.
Got it. And this is also something we see constantly. At least from my experience, when I read articles, we can see that policies are built around energy targets without respecting electricity systems and physics. Not at all. Could
Yes.
you comment on this?
Yeah, I think that is something I think very often about, and is one of the reasons I wanted to do broader work beyond just thinking about, power systems modeling and analysis, which is what I've done in the past. I think that the issue we run into here when we think about policy and electricity and our policymakers, our regulators not fully understanding it is you have to consider one, their background and the background of their staff. It's the vast majority, especially in the United States. We're talking about lawyers, economists at best. Some are just politicians with any sort of background who were just appointed because they were friends with the person who appointed them, or they had some other special interest or relationships. These are generally not people who have the expertise in the physics of electricity systems. That's not to denigrate lawyers and economists. They play an essential role in the electricity rate making process and the policy process. My own father has a law degree, so I have a huge respect for that. But that's part of the reason these more technical nuances are missed in policy and regulation conversations. And simply put, the staff that is designed to support these people also don't have those backgrounds. And unfortunately, what we've seen as historically, at least I would say specifically in the power and electricity industry, so we don't often have uh, really technical people who want to go off and do the work of communicating this information to the staff or communicating this information to the policymakers or becoming policymakers themselves, which I think is really the bridge that we need. We need more technical people in those policy making positions, in those regulating positions, instead of them just being at the periphery trying to influence. So that's where I think some of that comes from.
And let's hope that Latimer Enterprises will slowly start to change that reality
I
for
hope
us.
so. I hope
And from
so.
your experience, what are the most common misunderstandings about grid reliability when countries or, let's say, regions talk about high renewable penetration?
Well, this is a great question. So, my dissertation research focused on how do we integrate large amounts of variable renewable energy resources into power systems. And when I say variable renewable energy resources, a lot of the times we oversimplify what is renewable and what is not, and we try to eliminate certain things. But when I talk about variable renewable energy resources, I'm talking about wind and solar. So wind is variable in the sense that wind blows at different speeds at different times of the day. Solar is variable in the sense that the sun doesn't always shine at the same intensity, so panels can often convert the same amounts of energy into electricity. And so when you have variable renewable energy resources, they have their societal benefits, they have economic benefits in many countries too today, where we see where they're price competitive or where they are the lowest cost form of energy in certain countries. But the challenge is their variability. So how do you manage for variability? And that's something that grid operators have been trying to figure out in countries all over the world for the last decade. So we're moving to a paradigm where they can exercise greater control over these resources in a way they haven't been able to in the past. And asked about challenges. One of the key challenges is their variability, because it results in their not necessarily being the voltage support that the grid needs or the frequency support that the grid needs at different times. For example, sometimes there's too much wind and solar generation and it has to be curtailed or reduced in order to accommodate it properly onto the grid. So those are all of the challenges that grid operators try to balance.
And I would also add something that you've just mentioned before, especially policymakers, lawyers, those kinds of people who have some influence on how it's shaped. They tend to assume reliability is a software or pricing issue rather than a physical one, what we've just discussed, right?
Absolutely. It is essentially a physical issue. I mean, you cannot there are two duties of a EV power system, primary duties. First and foremost, reliability. Second is to ensure least cost generation ends up on the system. So reliability is crucial. When you think about these variable renewable energy resources from the perspective of a power grid operator, someone in power systems, you have to keep in mind that there are physical limits on power systems. The actual voltages on the power system have to be within a certain level. The transmission lines can only carry so much electricity, so much current really across them. So those limits have to be respected at all times. And when you think about it from a perspective of, being able to ensure that outages don't happen, well, grid planners plan for, scenarios where every every component essentially of the grid goes offline. What do they do in those cases? How do they bring the system back on? With renewable energy resources, you have additional challenges with high penetration renewable energy grids. So, yeah, like you said, reliability is an essential issue for variable renewable energy resources. That's not to say that there aren't solutions, but you have to keep in mind the challenges when you're doing the planning so that you can have the right solutions.
Agreed 100%. Now I'd like to discuss with you intermittency, firm power, and trade offs. So, if you could tell us when we talk about intermittency, firm capacity, and backup generation, what trade offs are policymakers often unwilling to acknowledge publicly?
When we talk about intermittency, it comes back to that idea of, like we were just talking about, variable renewable energy resources. They are both variable and uncertain. That's what makes up this idea of intermittency, that they are not always available. So when we say variability, the wind doesn't always blow at consistent speeds at every hour. When we think about uncertainty, you can think about it as not knowing necessarily which direction things are going to go. And when you bring that back to renewable energy systems, you can think about it in terms of, okay, do I actually know if the wind is going to blow at all today? Forget what's it going to blow. At what speed is it going to blow within an hour? Is it going to blow today at all? So that's the uncertainty piece. That's where we think about intermittency. And so that trade-off is that, okay, I have this resource that is low cost, that I can build relatively quickly compared to some of the other generation sources, but it also has these attributes that make it less than desirable, make it more difficult to manage. So how do I mitigate for that? Well, we need energy storage. We need massive amounts of energy storage, and we need long duration energy storage. Today, when we think about our long duration energy storage, we're thinking about lithium ion batteries that can store energy maybe at best for 8 to 10 hours. But what we really need are batteries on our power grids that can store energy for days or weeks at a time, so that we can really smooth out that variability and that uncertainty, and deploy variable renewable energy resources the same way in which we deploy firm uh, firm energy sources like your natural gas plants, which can ramp up gradually or to meet unexpected peaks, in order to support the system. So those are the different trade-offs you have to think about.
You've just mentioned the role of storage. So let's do a storage reality check. If you could tell us, because we know energy storage is often presented as the universal solution. So, from a grid scale perspective, where does storage genuinely help, and where is it being oversold in your view?
Where is it being? Oh, what? I'm sorry, was the last part?
Oversold. When it's like
Oversold.
hyped,
Yeah.
oversold to the public.
Yeah, I think it gets oversold generally as a universal solution. I think that's where it gets oversold, and I don't think people acknowledge the realities of the storage capacity. Like we were just talking about, how much energy can be stored, the length of time that energy storage can be stored for. So what long duration meant that 8 to 10 hour range, even at best. So we really haven't seen a lot deployed at scale that goes beyond that level. So that's something that the public simply just isn't aware of. Where it's useful are those short duration incidents, and there are plenty of those on the grid, in which we're seeing lithium ion battery storage, other chemistries that are starting to be used for more stationary storage coming online, and being an added benefit to both when they're paired with variable renewable energy systems, and when they're used on their own to support the grid with any of its other power or frequency or voltage needs. So they have a real role to play, especially in those supportive actions.
And many times, at least to me, it feels like storage gets treated as infinite, instantaneous, and cheap. But I think none of which are true, right?
I think you're absolutely right. The idea that storage is infinite, no, it's not true. Batteries degrade over time. They need to be replaced. You talk about it. I think you summed it up perfectly. There really are constraints on storage that we have to acknowledge, and we have to come up with additional solutions and pair it with other things.
And now maybe let's talk about less popular subject, which is transmission. So transmission rarely gets headlines, but it keeps showing up as a limiting factor. From your work, how serious is the transmission constraint and why is it so hard to solve?
I think it's a very serious issue, and I think you had a previous guest from Grid Strategies who I think did an excellent job of highlighting all of the issues. So I think listeners, watchers should go back to that as well for a more in-depth deep dive. But from my perspective, I think that it is serious because transmission is not just an enabler of getting more energy onto the grid, more generation onto the grid, but it is also needed because we have, at least in the US and other parts of the world, we have some very old transmission lines that have not been replaced and need to be replaced, and new ones should be added. And so, without those replacements, we risk running this equipment way past its useful life. So, transmission is a serious issue, and ign- I won't say it's been ignored. I would say it's been a difficult challenge to solve, not because it's a technological challenge. We know how to build transmission lines. There are companies today also working on superconducting transmission lines. So the next generation of what we have today, it's the challenge is really a policy and a finance issue. You have to have policymakers who have the will to write legislation that enables more transmission to come online. And you also need the financing in order to ensure that the transmission actually gets built, the transmission lines get built. And as part of the policy work as well, you need to get the public on board. You need to get people to understand the importance of transmission lines and that they're not just eyesores, as some people describe them. You have to dispel myths. Like some people still think that they're being exposed to radiation if they're near significant amounts of radiation if they're near transmission lines. You have to dispel those myths. You have to really work with people to get them to not see this as something that should not be in their backyard, quote unquote, but something that's an added benefit to them, their families, their businesses, their communities, etc.
And which country currently do you think leads research in transmission and has the most advanced technology? Is it still the United States?
I think that the United States has a ton of innovation that is ready to be deployed, but in terms of actually getting it implemented and deployed, I'm looking today at China as an example of being able to actually get those technologies deployed instantaneously. I think from an innovation standpoint, though, that the United States still has the leading engineers, leading companies that are ready to implement these solutions. But yeah, in terms of implementation, China.
Asking because it seems to me like it's one of the biggest gaps between climate ambition and execution at the end.
You're absolutely right. But again, I think when you look at what the Chinese are able to do in deploying massive amounts of renewable energy and enabling it with new transmission, the speed at which they're able to operate, no other nation is doing that right now. So I definitely think there are lessons to be learned from what they're doing for everybody. Even here in the U.S., we could learn some lessons.
You work with power system models. If you could tell us where do those models genuinely add value and where do they risk creating false confidence, for instance?
Yeah, so let's back up a second and make sure everyone in the audience understands the power system modeling process. So, power system models take the physical representation or what's actually on a power grid, they translate that into a set of abstracted components. So, we simplify what a transmission looks like, but it's a pretty accurate model. Not going to say that it's not. And then we translate those models that we've created physically into mathematical equations, and then we uh, use those mathematical equations to simulate how a power system operates. And so served us perfectly well for decades because they are first and foremost deterministic. They're generally highly accurate, especially those that use in what we call an AC formulation instead of a DC formulation. In an AC formulation, you're considering all of the real world constraints of power systems, like the fact that they have transmission lines and like that they have some very complex transformers, whereas in a DC formulation, you're ignoring those things. So that's one of the downsides of modeling. The AC formulation is can sometimes be more computationally complex to operate. That means that it might take a long time to get the result of a simulation. At least that's how it's traditionally been viewed. But now with cloud computing, that's much easier. Whereas with the DC formulation, it's generally been much quicker to solve and operate. And when you think about power systems that cover uh, whole countries or parts of countries, that's generally where you've seen the DC formulation used. So the inaccuracies that are modeled as part of that process really can abstract people from getting a real sense of what's actually happening on the system or how things will operate in practice. And you see those types of methodologies used in some of the software and tools that are marketed to developers, all sorts of generation sources. And so they sometimes, when they get into the interconnection process, they sometimes they're missing details and they think they got everything figured out because this tool that they ran, that advertised that it could, ensure that everything was uh, interconnection standards really didn't, because it misses some of the processes that real grid operators go through, some of which that they still do, manually on their own and don't necessarily always depend on software. That's changing, but yeah, that's power systems modeling and the complexities of it.
I'm also curious about assumptions that look reasonable on paper when you write them down, but then break down in operations. Do you
Yeah,
have any examples
I
in
do.
mind?
That I do. Thanks for bringing that up again. So the chief example that comes to mind for me is that more often than not, most power systems modeling processes treat the generation sources as purely deterministic. What I mean by that is that they are fixed in time. We know exactly what the output's going to be at every moment in time. But as we just talked about with variable renewable energy sources, or even things like hydro, we know that that's not true. For example, with hydro, there are droughts. With renewable energy sources, we've talked about the things that happen. Variable renewable energy sources, we've talked about what happens with them. But even with things like natural gas and other fossil fuels, they have their own uncertainties that aren't always properly modeled. So, for example, they have outages from time to time for a variety of different reasons. Sometimes those things aren't considered. So that's something that in the real world that actually happens, and one of the downsides of some of the assumptions models make today.
So again, uncertainty.
Yeah, uncertainty.
Now let's talk about policy design. If you had to point to one recurring flaw in energy and electricity policy design, what would that be?
I would point to the assumptions that we're always going to have all the people we need to do the work. I think that is a key assumption that I see all the time. I see currently in the discussion about meeting the demand for data centers. There's a lot of assumptions that there will be people to do the work. And by people, I mean the engineers who are needed to build, manage, and operate power systems. Policymakers don't build in workforce development sometimes into the legislation that they're crafting, or in the way in which they craft it doesn't build the right incentives to get new electrical engineers or new mechanical engineers, et cetera, interested in power, interested in energy so that they can do the work that's needed. So that would be the big thing that I think is missing: workforce development.
Thank you very much for those examples. Now, scalability. Looking at the next 10, even 20 years, so from 10 to 20 years from now, what types of solutions or system changes do you believe are genuinely scalable, even if they're unpopular or uncomfortable to talk about?
Yeah. So the funny thing is, I don't, right now at least, we never know how people will view some of these things years from now. But right now, the things I'm thinking of, I can't think of them as being unpopular. So I'll give you a few different examples. First and foremost, seeing the rise of microgrids over the last decade. And I think back to when I was just an intern at the National Renewable Energy Lab a decade ago, now the National Laboratory of the Rockies. Microgrids were still in the pilot phase. Today, we're seeing real utilities deploy microgrids for academic institutions, for militaries, in order to ensure that they have the ability to disconnect from grid when needed or operate fully islanded. There are different types of microgrid architectures, so that's something that I think will continue to scale. I think we'll see some real clear templates for how to build a microgrid, how to do it at scale over the next decade. The next thing I think about are digital twins, which is this idea that you can build a virtual reproduction of any physical component that might be on the grid. For example, you could make a digital twin of a battery, you can make a digital twin of a solar plant, a wind plant, etc. And what that looks like is you take onboard sensors, so sensors that are placed near these plants or whatever that physical object may be. They combine that with local computing that happens, local calculations that happen on that sensing device or on that instrumentation, and then works together with cloud computing, machine learning, in order to build that physical representation and predict how the device is really operating in real time. And so that will allow grid operators, planners, even the owners of these assets to really understand what's happening, what might happen to their assets, what's happening in real time, and then be able to make better and more informed decisions. So we are seeing today some pilots of that, but I think that will most definitely scale over the next decade. Those are a couple of examples that really stick with me right now.
I would say very down to earth example. So I'm pretty sure maybe we'll even see it in 5 years. We'll see.
Yeah.
And now maybe a piece of advice for decision makers and buyers. So for utilities, large energy buyers, or policymakers trying to make net zero aligned decisions today, what questions should they be asking? But maybe usually they aren't.
Yeah, I think there are a few questions they should be asking. First and foremost, I think they should be asking questions surrounding the trade-offs between the different objectives that they're trying to achieve. And what I mean by that is traditionally we've talked about in the discussion how the primary objectives of power systems were to reliability and ensure low cost, but now we've asked for sustainability. We've also asked for resilience, meaning being able to continue to operate in the midst of extreme weather and major storms. So as business decision makers, they really need to think about those trade-offs with more depth when they're approaching a utility, when they're approaching a policymaker, and think about, is our asset prepared in from all of these different dimensions. And then the second thing I would encourage decision makers to think about is to remember the workforce, which we just talked about a little bit earlier. Are there going to be the workers needed at the utility company in order to process our requests? We may need to build in some additional time for whatever our need is, because they're generally under resourced and they simply may not have the people needed. And then from the perspective of their own businesses, are they doing the things that they need to recruit bring the right people in to recruit, to ensure that their own businesses continue to prosper, so that whoever may be in charge of managing that asset in 10 years time will actually be there and be ready? And then are they making sure that they have the right processes in place to transfer the knowledge down to that next generation of people? Those are the things I would think about.
And if there's one question, so we can choose only one, they should put on every slide deck or RFP, request for proposal, what would that be?
Yeah, I would say they should always say, do you have the people needed to do the work? Because at the end of the day, all the questions I think about today come back to who is going to do the work, plain and simple.
Got it. Before we wrap up, is there anything we didn't touch on that you think is important or worth highlighting for our audience?
No, I think we've had a really substantive discussion and really appreciate it. I just again encourage the audience to think about that question, and to really consider all of the trade-offs that come with electricity systems.
Thank you so much. Naeem, this was a refreshingly grounded conversation. At Net Zero Compare, we focus on cutting through hype and understanding what works within real world constraints. And this discussion fits perfectly into that approach. So thank you very much for sharing your perspective and for bringing technical honesty into a space that often avoids it.
Thank you so much. It's been great.